Welcome to the deep dive. Today, we're tackling a question that's really central to how these advanced AI systems are evolving.
Right.
When do they actually start to think for themselves, learn from their mistakes?
hmm
We're diving into this concept called reflection in language models. Basically, their ability to look at information, check their reasoning, and, adjust what they do next.
It's a really critical piece for getting to more sophisticated problem solving.
Exactly. And I think for anyone listening who's really trying to learn about this stuff, it's fascinating.
Absolutely. And what's really interesting, I think, is that for a while, the common thinking was this self-correction ability. It mostly showed up during reinforcement learning.
Yeah, that feedback stage, right?
Precisely. That's where everyone thought the magic happened.
Okay, but this is where things get interesting. We've been digging into this paper from Essential AI, Rethinking Reflection in Pre-Training.
A really insightful piece.
And their argument kind of flicks things on their head. They're suggesting the groundwork for self-correction is actually laid way, way earlier during pre-training.
During that massive initial data learning phase. Yeah, it's a pretty big claim.
It feels like a real aha moment, challenging what we thought we knew.
It does. So our mission today really is to unpack this research. We want to get into their innovative methods and figure out what these findings mean about reflection showing up so early.
Specifically during pre-training. Okay, let's get into it. How did they even start looking at this?
Well, first off, they realized they needed a sharper definition of reflection.
Right, because just checking if the final answer is correct, that doesn't tell the whole story, does it?
Not at all. It doesn't tell you if the model actually reflected or just got lucky or maybe used a flawed process to get the right answer anyway. So they built a more, let's say, nuanced framework.
Okay, tell me more about that.
So a key thing they did was distinguish between situational reflection and self-reflection.
Situational and self. What's the difference there?
Situational reflection is when the model looks at reasoning or info that comes from outside, like maybe another AI's work or some text where an error was deliberately put in.
Okay, so evaluating external stuff.
Exactly. And then self-reflection is when it examines its own thinking, its own output.
Ah, okay, that makes sense. So it can critique others or critique itself.
Precisely. And separating those helps you analyze the ability much more closely.
And they break it down even further, didn't they, into explicit and implicit reflection.
Yes, that's another important layer. Explicit reflection is pretty straightforward. The model actually says something like, wait, there's a mistake here, or this step is wrong. It flags the error in its output.
Even if it doesn't fix it correctly in the end.
Interestingly, yes. The key is that it identified and articulated the error. Implicit reflection is subtler.
How so?
Here, the model gets the right answer, even though it was given bad or misleading information, but it doesn't explicitly call out the error. You sort of infer that reflection must have happened because it navigated around the problem successfully.
Got it. So one is stating the error, the other is just getting it right despite the error.
You've got it. So with these definitions locked down, they needed a way to actually test for this early reflection.
Because, like you said, just using standard benchmarks probably wouldn't cut it. You wouldn't see this behavior often enough, maybe.
Exactly right. Reflection can be pretty rare in normal data sets. And other research has shown that different models make different kinds of mistakes, so their reflection patterns vary too. It's messy.
So standard tools weren't sharp enough. What did they do instead? This leads to their really innovative part, right? Creating these adversarial data sets.
That's the core of their method. They came up with a really clever way to programmatically mess with chains of thought or coaches.
The step-by-step reasoning models use.
Exactly. They deliberately injected errors into these reasoning steps. Things like bad math, logical contradictions.
So creating adversarial cooties, basically setting traps for the model.
In a controlled way, yes. It forces the model to confront errors, giving it a clear chance to reflect. They mean exactly what kind of error was introduced and where.
That sounds really smart. Can you give a quick example, like what kind of math error?
Sure. So imagine a word problem where the reasoning should be, say, 2 plus 2 equals 4. In their adversarial QT, they might change it so the step says 2 plus 2 equals 5.
Ah, okay. Obvious, but forces the model to notice if it's paying attention.
Precisely. Or for logic, maybe a step contradicts something stated earlier in the reasoning. Clear inconsistencies.
And they tailored these adversarial examples to test both kinds of reflection, situational and self.
They did. For situational reflection, they had a really powerful model, like a GPT-4o or similar, generate the reasoning with the errors. The model being tested then had to evaluate this external, potentially authoritative, but flawed reasoning.
Okay, see if it could spot errors from a supposedly smarter source.
Right. And for self-reflection, the approach was different. They'd first let the test model try to solve a problem. If it made a mistake and generated flawed reasoning.
They fed its own mistake back to it.
Exactly. That flawed reasoning became the input for its next attempt, a direct test. Can you spot your own errors?
Wow, that's quite thorough. And they didn't just test this on one type of problem, did they?
No, they were careful to cover different ground. They created 6 different data sets across mathematics using GSM-8K and a harder version, GSM-8K Platinum,
Okay.
dot coding, using crushable benchmarks, logical reasoning with big bench hard tasks, and even knowledge retrieval with trivia QA.
So math, code, logic, knowledge. Pretty broad. That makes the findings more convincing if they hold up across the board.
Definitely adds weight to the conclusions.
Okay, so great setup, precise definitions, clever testing method. Now for the main event. What did they actually find? What's this big insight about reflection happening early?
This is really the headline finding. They found strong evidence that both situational and self-reflections start showing up during pre-training, not just after reinforcement learning like the old view suggested.
Much earlier than we thought.
Much earlier, it suggests these abilities are more fundamental, maybe emerging naturally from learning patterns in massive data sets.
That is a big shift. What kind of numbers are we talking about? How often did they see this?
Well, the numbers were pretty striking. Across all the different data set and model checkpoint combinations they tested, they saw situational reflection in 231 out of 240 pairs.
Wow, that's nearly all of them.
It's very prevalent. Even self-reflection, which they found harder for the modeled, showed up in 154 out of the 240 pairs.
Still more often than not. So these pre-trained models, even before fine-tuning, have some capacity for this.
That's what the evidence strongly suggests. And crucially, they didn't just look at the final pre-trained models.
Right, you mentioned checkpoints. They looked at models during the pre-training process.
Exactly. They evaluated checkpoints from different stages of training for models like OLMO2 and QN 2.5. These families cover a huge range of sizes, too. OLMO2 from 7 billion up to 32 billion parameters, QN 2.5 from tiny half-billion models all the way to 72 billion.
So they could track how reflection developed as the models got bigger or trained on more data.
Precisely. They could see it emerge and strengthen over the course of pre-training.
Okay, that naturally leads to their next big finding, then the link between pre-training compute and reflection improving.
Yes, they found a pretty clear correlation there. More pre-training compute, which is basically model size times the amount of training data.
More parameters, more tokens.
Right. As that compute number went up, the models generally got better at reflection. They quantified it too. An average Pearson correlation of 0.76 between accuracy on these tricky adversarial tasks and the log of pre-training compute for the OLMO2 models.
0.76, that's a strong positive correlation.
It is. It really suggests that investing more compute in that initial pre-training phase directly helps build these reflective capabilities.
Can you give an example of that? Like, how did more compute help on, say, those math problems?
Yeah, the GSM-8K Platinum results showed it clearly. As the OLMO2 models got bigger and trained longer, meaning more pre-training compute, they solved more of those adversarial problems using explicit reflection.
So they were more likely to actually say, hey, that step is wrong, and then fix it.
Exactly. More compute seemed to lead to more explicit error identification and correction, not just implicitly working around the error.
That makes a certain kind of sense. A more thoroughly trained model has a better grasp of the rules, maybe. And this pre-training investment, it pays off later too. Less work needed at inference time.
That's another interesting implication they point out. Models with more pre-training compute often needed less complex prompts or fewer inference tokens to perform well on these tasks later on.
So like a trade-off. More compute upfront means potentially more efficient use later.
It suggests that yes, investing heavily in pre-training might make the models more inherently capable and require less handholding at inference time.
Okay, now one of the things that really jumped out at me was the wait trigger. Just adding the word wait could make models reflect more. That seems almost too simple.
It does seem surprisingly simple, doesn't it? But they found that adding simple trigger tokens like wait could noticeably prompt even partially trained models to reflect more.
What difference did it make? How did they measure that?
Well, again, looking at the GSM-8K Platinum math problems, they found that while models could sometimes reflect implicitly without any trigger,
Just figure it out silently.
right, but adding wait significantly increased both explicit reflection, they were more likely to say there was an error, and their overall accuracy on the problem.
So that tiny word makes them pause and double check.
That seems to be the effect. The paper even models it in a fascinating way, suggesting the effect of wait is like a mix between having no trigger and having a trigger that explicitly says, I made a mistake, let me rethink.
Huh. So it nudges the model towards its own latent error-checking ability.
That's a good way to put it. It seems to amplify an existing, if sometimes dormant, capability.
Now, you mentioned earlier that self-reflection was harder for the models than situational reflection.
Yes, that was a consistent finding. Fewer models demonstrated self-reflection compared to situational. suggesting it's a more challenging cognitive leap, so to speak. Critiquing yourself is harder than critiquing others, perhaps even for an AI.
But did that ability also improve with more pre-training? Did they get better at spotting their own mistakes over time?
They did. Despite the difficulty, self-reflection also improved with more pre-training compute. The models, especially the larger ones later in training, got better at explicitly identifying their own reasoning errors. They showed an example with the Cruxeval coding benchmark where this trend was clear.
That's encouraging. It suggests maybe there's a developmental path there. Perhaps recognizing your own errors comes first, and then fixing them follows.
That's a plausible interpretation. The research certainly paints a picture where these foundational self-awareness skills start forming and getting stronger during pre-training.
So taking all this together, what are the big implications? If reflection starts this early, how should that change how we train these models?
Well, it definitely opens up new possibilities. If pre-training isn't just about absorbing data, but also about developing these core reasoning skills like reflection, maybe we can design pre-training strategies to specifically encourage it.
Like feeding them certain kinds of data or structuring the training differently?
Exactly. The paper explicitly calls for future work on that, trying to figure out how these early germs of self-reflection, as they put it, can be nurtured better, and identifying what kinds of data distributions actually promote self-reflection during pre-training.
Finding the right food for thought, essentially.
You could say that. And they also touched on something called a local consistency bias. What was that about?
Ah, yes. They noticed, especially early in training, that models sometimes stick to an answer that seems consistent with the immediately preceding flawed reasoning step, even if it leads to a wrong final answer.
So they get stuck in the faulty logic locally. Kind of. But the good news is this bias seemed to decrease with more pre-training, particularly in the bigger models, suggesting that more compute helps them build a more global, correct understanding rather than just following the local, flawed path.
Okay, so summing up this deep dive, the huge takeaway seems to be that reflection, this ability to self-correct, isn't just a late-stage add-on. Its roots go deep into pre-training.
That's the core message. It really reframes how we should think about the developmental trajectory of these AI systems. It's happening much earlier, more fundamentally than we perhaps appreciated.
And the way they figured this out, using those adversarial data sets, that's a big contribution in itself, right? A new tool for the toolkit.
Absolutely, it's a methodological innovation that gives researchers a much better lens to study these subtle but crucial reasoning abilities.
So as we finish up, it leaves you with a pretty big thought. If these core reflective abilities are emerging so early, almost naturally from the pre-training process, what does that really mean about the potential intelligence baked into these models from the start?
Right. Could pre-training, if optimized correctly, unlock even more sophisticated reasoning than we currently see? It definitely pushes us to think differently about where the limits are and how we might reach them.
A very provocative question to ponder.
It is, and of course this discussion is just scratching the surface. We definitely encourage listeners to check out the Essential AI paper itself and related work. There's so much happening in this space.
Absolutely a fascinating area, and this paper adds a really important piece to the puzzle.